To dive right into it, I'm Andrew Therriault. I'm the Chief Data Officer for the City of Boston. I lead a team of about 20 people, mix of data scientists, engineers, performance analysts, GIS specialists, people covering a wide range of different analytics and data science related areas. Prior to this, I did a PhD in political science. I did consulting in the data science world for a few years, and then most recently, before my current position, I was head of data science at the Democratic National Committee. So I've worked on a bunch of different projects across a wide range of fields, and I'm going to talk today about some of them that I've worked on, because I've made a lot of models in my time, and I've made a lot of mistakes. I think that's something that anybody who's done this for a while will understand, that that's how you learn. And so what I want to do today is to share some of the things that I've learned along the way through a lot of trial and error, and hopefully you can use them in your own work and find them beneficial. So what I'm going to talk about is what I call sustainable machine learning models. And what I mean by this are models that use the outputs of one run of the model to generate the training data that's used to update the models in the future. So some of the examples of what this might look like. An obvious one is recommender systems, which I think a lot of you in the data science world are familiar with, where you take what you know about a particular audience and you recommend them, whether it's a product or a TV show to watch or what have you, but then you get data back. You learn what they clicked on or what they bought, and you can use that data to improve your model. Similarly, if you're trying out different kinds of ads or targeting different people with marketing and so forth, all of these things are areas in which you can use the results of your model to generate training data. And that's a special class of models that I'll dive into and explain why they're unique and what kinds of best practices you should take as you go into this world. So what exactly is different about these kinds of models? Well, to start off, set the precedent, I think this is going to look very familiar to anybody who's done machine learning. This is a pretty traditional process. You start out by collecting your data, you process it, you train a model, you validate that model, and you make a prediction. And maybe you put it into production and you slap an API on top so you can generate predictions as needed. Maybe you go back and get more data later and run through the process again, this time in a bit faster method. But the point here is that your data collection is independent of the last step of the predictions. By contrast, in what I call a sustainable machine learning model, there's two different steps. So the first thing is this last sixth step, deployment, where you're actually using the predictions you generate. So that might be targets for people to contact or direct advertising to. It might be recommendations for products or movies or what have you. It might also be something like a recommendation for somewhere to inspect or audit, something about data quality, something about, for example, in the city of Boston, we use a similar system to target our restaurant inspections. These are all kinds of things where you're taking these predictions, you're immediately putting them out into the world and using them to feed back into that first step, that outcome and feature collection. And then the second thing that's different here in the process is the retraining and revalidation steps, where because you're doing this over and over and over again, you will often end up handling those differently than you would if you were just doing it the first time through. For example, by automating some of these processes, or simply building into your productionization automatic updates as they go in a way that will alert you if something goes wrong, but doesn't require you to have hands-on keyboards every time that this gets updated. So why is this really that big a deal? Well, a few things. One, there's really no perfect way to optimize for something like this. If you're just trying to build a one-off model where your only goal is the best accuracy possible, the best fit in that one time you run through, that's easy. We've got plenty of metrics for that. Anybody who's spent more than 20 minutes looking at scikit-learn has probably dug into, the metrics module and really come to understand a lot of things through there. But, there's no one metric for something like this, because you're getting into the world of what's called the exploration-exploitation trade-off. Any of you who've done work with experimentation, particularly getting beyond just basic A/B testing into things like multi-armed bandits, you're probably familiar with this idea that you're optimizing on several things. You want to do as well as possible right now, but you also actually want to learn. And so there's actually a benefit to not exploiting your model fully in one moment, because if you make errors, you learn from them going forward. And ultimately, there's no perfect formal solution for these kinds of models. It's a very, I hate to say it, but artistic process in a way, because no two models are going to have the exact same solution. And maybe someday somebody will come up with a a better approach for this, but from my own experience, it's been a lot of trial and error and figuring out what is really the right way for any particular application to deploy a model like this. And then the last thing that's worth noting too is that, once you're getting into this world of building these models that are continuously updating and improving over time, you're building software, which is just a very different paradigm of programming, beyond what your typical data science intro would teach you. So you're thinking about things like version control and automation and scheduling and continuous integration and setting up alerts to, in case your models start performing much better or much worse than they had before, which might be a sign something's wrong. So you have to consider a lot of these different things as you go, not just, the basics of making a machine learning model. So here I've got a framework that I would recommend as a starting point. And some of these things can vary depending on your particular use case. But I found this to be a useful way to approach these kinds of models. First step is research design. That's something I note here is a manual process, pen and paper. Doesn't literally have to be pen and paper. But the point here is that before you ever start to code, it's critically important, as it is in every data science project, but particularly in these kinds of models, to think about what your research design is in that, what are you predicting? What is it that you're modeling? What does the data generating process looks like? What is the application? How is this going to be sustainable over time? Before you ever start writing code, it's important to think about these, and particularly so in models like these, where, over time, if you're not paying attention, things can get worse and worse and worse. And often these are the kind of models you use for critical processes and infrastructure and so forth in any data-driven organization. Once you get through there, you go through your pretty standard process of development and then productionization, and then you deploy. And when you deploy, again, as I mentioned earlier, that's the point where you take those predictions that come out of your model and you put them in some process in the real world that's going to eventually lead to those new results that feed into a retrained model, which goes back and gets deployed again. And that's the cycle of sustainable models. And every so often, you need to go back and do true revalidation. You might build in some automated checks just to make sure things are working as expected as you go. But with a model like this, I would highly recommend that every so often, whether it's every day, every week, every month, you actually go back and do it as if you were doing it for the first time. Make sure the model makes sense, that it's doing what you're expecting, that the patterns you're seeing are the kinds of patterns you would expect given the model design that you have. And if you find that either something's not working right or you just spot some opportunity for improvement, that's when you go back to development. That's when you go back and say, well, the model could be better. I'm going to make it better. And that's a key thing in these models. They're never done. As long as you're using them, they are not completed. If they're completed, you're missing out on opportunities to improve because there's always ways to improve in these. So the critical thing in making a sustainable model work is what I call diverse data. And the context here is that the reason you would make a sustainable machine learning model, which generates its own training data more or less, is that you get that for free. You're not incurring costs to go out and do independent data collection. So just as an example from my own work, I did a lot of work in politics where the typical process for making a model would start out with a survey. You'd go out, you'd survey 5, 10, maybe 20,000 people, and you ask them some questions, and you have information from, say, a voter file, from consumer databases, from voter contact histories, and so forth, and you would use that to generate a model that you can use to create predictions for every other voter in a state or in the country. We used to do that all the time. We'd do it for things like not only who are you going to vote for or are you likely to turn out, but we'd also think about things like modeling demographics or issue positions and how likely you are to become a volunteer. These are all different kinds of political models that we make, and the ones that are based on surveys, they involved a lot of cost up front. And you can't always do that in terms of just having the resources to go do original data collection every time you want to update a model. So the benefit in these sustainable designs is that you get that information basically as just an organic part of the process. The trade-off here is that the data is not as good. It's not, this perfect random sample you might get if you go out and do a survey. Instead you're getting data which there is bias baked into because you're not going out and collecting data at random. That's the whole point of doing targeting or tailored ad content or what have you. You're not doing it at random. This is that exploration exploitation trade-off I was talking about. The key here is that these biases, if you're doing this right, can be overcome. And there are two basic things you need to think about. One is coverage, namely that if you focus too narrowly in one particular area, for example, if you are doing fundraising targeting, which that was one of the biggest models I made at the DNC, that we directed all the voter direct mail fundraising. So if you've received mail from the DNC in the past couple years asking for money, I'm sorry, that was me. Basically, this was like one of the most important models we made. And the thing is if you just drill down in a really narrow set of targets, the problem is you don't learn about all the people you're not asking. You don't learn what they would do. And I'll talk more about that in a minute. But the point here is that, your model is not going to be sustainable if you don't have enough coverage to make your model change course over time and try new things. The other part is reliability. And again, I'll give a very practical example of this in a minute. But the idea is, you're putting these predictions out into the wild. You're generating data which isn't necessarily coming from the same process that you might find if you were to just be randomly casting about and collecting original data. There's some bias baked into this, and if you don't understand the data generating process that you're using, the issue that will come up is that the data that you have will not be an accurate reflection of the data that you don't have. The relationships in the real world, if they're not reflected in your data, it can lead you to wrong conclusions. So just to illustrate, and I should say all of these slides, I've already made it available. They're on my GitHub page. I've linked to them from Twitter, so no need to write everything down, and I may breeze through a few of these, and you might want to go back and check in more detail. But so the first example, when I was talking about coverage, is when you're talking about narrowing down to some kind of target universe, like for fundraising, or say if you're directing different kinds of advertisements or different kind of recommendations. If you find early on, hey, this group of people responds best to our fundraising appeals, or this ad works way better than the other ad, and you just focus on that, then what's going to happen is you're not going to collect any kind of information that would change what you think and what you do. So in this example, these are just very token, non-real data examples. But basically, there's 3 different clusters of potentially good targets in here. And what happens is the first time you run the model, it finds one of them. And the next time you run the model, it just drills down into that one again and again. And it's ignoring these other potential areas. And in the real world, one of the ways this can look like is when I started doing direct marketing targeting at the DNC, there was actually a rule in place that nobody would send mail to somebody who hasn't already donated if they're under the age of 65. And this was based on findings from earlier targeting, which found, well, hey, look, it makes sense from a logical point of view that people who are of retirement age are more likely to read their mail and respond to it. So yeah, I can see where somebody got that idea that they sent out a bunch of mail and found that people 65 and up were donating at much higher rates. The problem is they stopped mailing anybody under age 65, and well, there's a sustainability problem when you are soliciting new donors who are over the age of 65. It's a limited population, and that wouldn't be such a big deal if we were a really small nonprofit sending out 5 or 10,000 pieces of mail. We were sending out anywhere between 1 and 5 million pieces of mail every month. So we can exhaust that population really quickly. But the other thing, of course, is once they get on your donor list, they don't necessarily stay on that donor list for that long. So the long-term value of those new donors you're bringing in actually isn't as great as if you get somebody to become a first-time donor when they're in their 30s or 40s or 50s. But what we found is, I came into this and said, what, let's relax this. Let's walk it back. We didn't have any data from anybody under the age of 65, but we said, well, what, let's basically effectively treat those people as the bottom of that age range, see what happens. And turns out the first time we sent mail, our best performing age group was 50 to 64. Because in part, we'd exhausted all the good targets from 65 and up, because this was the non-donor targets. Once they donated for the first time, they were taken out of that universe. So it turns out over time, what had happened was actually a different age range was better because we'd exhausted all the good targets. And we would have never figured that out if we had only focused continually on that one particular age range of 65 and up. The other problem you can run into is if you put too much stake in data that's generated from a biased process. And here we've kind of got the opposite situation. We actually have a pretty clear pattern if you can see all the data. But what's been observed so far is actually a non-random set. And so the model here says, well, OK, we find these 3 clusters. So let's focus on those. And it keeps trying to focus on those and ignores that broader pattern that's actually there. In a way, it's the opposite of what we saw before. It may focus specifically on these different areas, but it's relying too heavily on data that actually, that in practice it's not performing the way you expect. So one thing that we worked on a lot at the DNC, another kind of sustainable model, was for volunteer recruitment. This is a model that we put together for campaigns to target people who could potentially become volunteers. And the dirty little secret of it is it was a way to get campaigns to share volunteer lists with each other, because campaigns are generally terrible at that. Not only are they very protective of it, but generally the day after an election, all the staff goes and gets another job. So oftentimes there isn't even anybody to ask after a campaign for permission. But at the DNC, we put into effect a data sharing agreement where after a campaign, we could pool these volunteer histories together and then use them to create this model. And what it did was it basically looked and found people who not just looked like volunteers, but were people who, if we were to ask them to volunteer in the future, would be likely to say yes. And when I first ran this, what I ran into was a case where I could have sworn I had basically coded something backwards. Because what I found is in the population I was looking at, the best targets were actually Republicans. And first I thought I just made a mistake. I assumed I coded something backwards. And then I tried to rationalize it, and I thought, well, maybe it's that say people who are older and more settled down and live in the suburbs, maybe they're just more likely to volunteer because they live that kind of lifestyle. And so it's the Democrats who look more like Republicans in terms of demographics. Maybe they're the ones who are most likely to volunteer. And I started digging into this more, and that was bullshit. What I actually found was that this was a bias problem in the model. That the problem is I was building a model which was based on attempts to recruit volunteers. And here's the thing. The only time a Democratic campaign is going to attempt to recruit a Republican to be a volunteer is if they actually have some other information that suggests they'd be a good target. Like they signed up for your mailing list, they made a donation, they showed up at an event. They may be registered as a Republican on the voter file, but they've done something to show the campaign that they're actually supportive. Otherwise, it wouldn't make any sense at all to ask a Republican to become a volunteer. So what was happening was that the model was looking at this biased data and saying, well, Republicans are actually great Democratic volunteers. Let's ask more of them. And of course, that's not how it works. So in this case, the solution wasn't anything fancy. We just finally had to realize, let's just drop the Republicans from our training sample because it's obviously an outlier. But that's the point I'm trying to make here, that sometimes if your model can get too caught up on these biased data generating processes, you can actually ignore the real patterns that are in there and get too focused on things that don't really work once you extend them out. And the important thing is you're going to make mistakes like that. Some of them might not be so obvious, but even in that case, you should make sure your model is open to change. And if it doesn't work the way that you intended, it picks up on that and changes its predictions going forward. So how do you make your data diverse? Well, here are 5 options. And they roughly go from, at the top here, a sort of research-focused approach of deliberately collecting more widely applicable data, all the way down to building something into your model which allows for you to collect diverse data without actually going out of your way to do specific research data collection. So the first one is what I call broad-based sampling. And that's basically just sort of bridging that gap between pure research data collection and collecting it organically through your process. So in our restaurant inspection models in Boston, we send inspectors out to go to places that we think are likely to have violations. But we also have regular annual inspections between 1 to 3 times, depending on the kind of establishment. So every place basically is going to get checked at least once a year. So what that does is it introduces new data from places where we don't have any reason to think that they're a good target for inspection, but we're going to do it anyways. So what that does is it keeps a diverse data pool in there so that, if we find that, hey, there's a particular kind of restaurant or a particular characteristic that actually predicts food safety violations really strongly that we haven't been accounting for, that will make its way into our data. The second is supplementation, bringing in outside data that can help create more variety. So when we were doing fundraising, we would not only take our, the targets that we were identifying through our model, we would also target people who came in from outside donor lists from other organizations, things like, say, Emily's List or the Democratic Congressional Campaign Committee. We might share lists with them, and so we add people in. The trouble here, of course, is that's, again, there's a bias in that selection. We have to account for that. That can be taken into account in your model to some degree. You just have to take things with a grain of salt and build that into your feature set. But what it does, it allows you to bring in information about people or about other circumstances or whatever it is you're modeling that you wouldn't otherwise be getting if you just relied on your model's predictions. The third is what I call waiting to learn, and that's trying to build in this learning into your process. So remember I talked about the exploration-exploitation trade-off and how hard it is to make metrics. Well, here you would deliberately prioritize instances where you need to get more information. So what that might mean is, when you're establishing a target list or you're picking which ad to show somebody or anything like that, you incorporate directly the uncertainty in your current prediction as a way to prioritize collecting new information in cases where you have a lot of uncertainty. The fourth of these is what I call rough targeting, and this is probably the most hacky solution here, but it actually works. So the first time we rolled out those volunteer models that I mentioned a few minutes ago, we had them to whatever level of precision we needed, but what we realized was, well, if we put out what is typical in politics, which is you put out a score of somewhere between 0 and 100, and maybe either rounded or with one decimal place, what's going to happen immediately is every campaign who gets access to this is going to go and contact the people with scores of 100. And those people's phones are going to blow up and they're never going to answer them again because they got called by every campaign, within 100 miles on the same day. And so instead, what we did is we realized, well, there's two things here. One, we just don't want to blow up the list and make it not work anymore. But also, we wanted to collect more data because this was the first iteration. And so what we decided to do was to round the scores. So the first iteration of this, we actually made it a 0 to 10 score and rounded them so that basically, and these are ranked scores. So, 0 was basically Republicans, or likely Republicans, and you had deciles of 1 to 10 among the likely Democrats. And so what happened is the top targets, it was actually a pretty broad group. They were still, top 10%, but the campaigns weren't able to distinguish between those. And so what it did is it forced them to bring in people who, they weren't the bottom tier targets, but they also weren't the very top based on our model. And so what that meant was we got a pretty wide swath of the electorate. So the next time we did this, we were able to make the model better and better and better because we were getting pretty wide coverage. And the last of these is what I call high churn modeling, which is you don't actually go out of your way to collect diverse data, but the thing you do is you make sure that as soon as your model doesn't work the way you plan or you learn something about a particular case or a particular individual that makes you want to change your prediction, you make sure your model will respond to that. So one of the things we did was phone quality scores. This is what the DNC used to assign what the best phone number is for any given individual in the country. There are about 200 million or so active voter registrations in the country. A lot of those are outdated. There are only about 160 million actual registered voters. But in any case, for those 200 million active registrations, we had about 500 million phone numbers. So you need to figure out how to match them up. And what we did is we built models for any given combination of those two. We basically would come up with a prediction of how likely it is that it's a working number and that if somebody answers, it's going to be the person you want to get on the phone. And so the thing we did with this model is we built it to rerun every night with the results of all the day's calls made by every campaign in the country that was using the central voter contact software. So by the leading up to the 2014 election, we were talking about 10 million calls a week were filtering into this system. And what we would do is, as soon as we would get a case where, if I tried calling Ben over there and found out his number's been disconnected, but I have another number for Ben, unless I know that number is also terrible, what's going to happen is within 24 hours, I'm going to swap out the new number for the old number. And so the next time somebody tries to call Ben, they'll be calling on a different number, and we'll get information about that. And maybe that number sucks too, and we don't have any good numbers, but at least then we know, okay, this is a person we don't have any good numbers for. Let's go out to our consumer data partners and source a new phone number for him. And that allowed us to really turn that over quickly. And it also meant that, if our model was making predictions like the number it said was best isn't best, that was corrected very quickly. So finally, to wrap up, I just want to offer a few basic recommendations for making these sorts of models. One is in terms of features. The key here is building in features that create heterogeneity in your predictions, that you don't just, as I mentioned earlier, drill down into one particular area of your feature space. So some of this is incorporating things like cyclical patterns over time, but you also want features that will change, whether that's truly dynamic features, from external sources that can change on a regular basis, or things like component models where you build in things like models of, say, demographics. We built in models of like language preference and household composition and marital status and so forth. And we updated those models regularly. And so that would add some variety into our other models that, when we would rerun, we'd have variation in the predictions, which meant we would end up trying out more of the feature space over time. But I think most important is incorporating individual histories. So that example of Ben's phone number, when I try to call Ben, I want to make sure that feeds back into the model, because that's something where I don't just want to fix the model. I want to make sure the model fixes its own predictions, because that's the whole point of doing these sustainable models. The outcome of the model is also your data generating process. And so by doing that, you don't want to just make a better model. You want to make better predictions for the individual cases that you're predicting for. Second part, when you're actually building the model, you want one that's going to incorporate the complexity of different kinds of interactions between your features, incorporating things like nonlinear patterns. That's why I'm a huge fan of tree-based models for these sorts of things. Using ensembles, retraining frequently, all of these things are based on the idea of, every time you run the model, you should get different predictions. That's what allows your model to change and improve over time. And it also allows it to try more of the possible feature space to keep your data diverse. And then lastly, evaluating your model as you go. I like to do what I call out-of-context validation. So this is different from your typical out-of-sample validation, where you just hold out something that's generated from the same data generating process. I think particularly for these kinds of models, it's actually much more important to make sure that they work outside of the data you're using for training. So for example, rather than, if we're doing fundraising models, rather than just holding out a random 10 or 20% of the total set of fundraising mailers that we had sent over the past year or two, what instead we would do when we were testing out the model to make sure it works is we'd hold out the most recent couple months and build a model based on the data up until then. And so that was the proxy for what we were actually trying to do, which is predict how something's going to work in the future. And that ended up telling us a very different thing, because it meant that any patterns that changed, we didn't have any data to tell us what the temporal patterns would be beyond what was in that initial training set. And we would do this as a two-stage model. Obviously, we'd retrain with all the data after the fact, but to just make sure that everything we were trying to do was working correctly, we do that pretty extensive validation. Also, going forward, you do need to stay on top of things, track how your model's doing over time, be willing to change it. And I think one of the things that's really important is, your model should either stay about the same or get slightly better over time. If it's getting worse, you probably want to mix something up, try something new. It might just be that you're using a algorithm that's not covering enough of the feature space, say, or you want to add some more variety in your data. But also be worried if your model gets too good. because it might mean that either there's something wrong in your model or your balance of exploration and exploitation is a little off. I think models that predict too well are probably the worst case scenario. I'd much rather have a model get worse than get dramatically better, because that often means data leakage. So particularly be on the lookout for that, and make sure that you've built that in your system, particularly if you're going to automate. So the final bit, I think this applies to all of machine learning, but especially for these kinds of models. First, understand your data. Understand what that means in the real world, what the data generating process is, how your data and predictions are going to be applied, and make sure you have an understanding of that before you start making a model, because ultimately if you're making a model of something you don't understand, your model is going to be terrible. So don't do that, please. Second one, sanity checks. I'm not the sort of person who thinks machine learning should be telling us a lot of things we could never figure out on our own. I think machine learning works best when it's common sense at scale. Namely that, what computers are good at is synthesizing a ton of information all at once and using that to generate a very simple prediction in the end. With our restaurant inspection models, for example, we use basic things about restaurant characteristics and inspection history and so forth. We also do things like bring in Yelp reviews. And we don't expect every restaurant inspector to read, every Yelp review for every restaurant in their area every week. But a computer can do that just fine. So that's really where we add a lot of value. And figuring out how to take all those things and combine them into one prediction, that's where computers are really good. If you're getting results that don't make sense to you, I would be really skeptical about your model. I think those kinds of basic sanity checks, even if you can't understand all of the causal relationships or it's not a very simple linear relationship in your model, it still should make some kind of sense. Look at things like, what's the distribution of predictions across the distribution of features and so forth. Build in some basic things along the way. And then finally, you're going to screw up. Every one of these models is imperfect, as is every model, obviously. But these models are hard. You're going to need to change them over time. Best case scenario, you make a model that's okay generally from the start, and then you have opportunities for improvement. But be aware, you'll probably screw something up along the way, or something will change in the underlying data. When we were doing fundraising, we had one round where our model got way better, and the problem was that turns out we were sharing fundraising lists with this consortium that was generating this consumer data file that we were happened to be using in our work. And we had started doing that a few months after I started making these models. So all of a sudden, from one month to the next, these consumer data features started getting really powerful. Turns out it's because there was data leakage. I didn't recognize that they were actually incorporating our results, but they turned out to be really, really great predictors. And that kind of stuff just happens. So be aware of it. Don't stress about it. Just be on the lookout and make sure you pay attention. So with that, we're just about at the end, but if anybody has any questions. Yeah, Sean.
Some really great advice there. I'm curious, since you've built so many models, could you help us get a sense of the median amount of time that is typically required to dissect what went wrong in a model, and then the median amount of time needed to take action to then go back into that cycle?
Yeah, median is a good stat for that, because I would say hours. This was something when we were doing the fundraising models, for example, we would send a big mailing once a month. And so at least once a month, I had a night where I was just pretty much resigned to being on my couch till 5 a.m, like doing all the runs, because ultimately, something would always go wrong, and I needed to kind of babysit as it went the night before we actually cut the final list. And so, sometimes it's really simple. Sometimes you understand what's going on. Sometimes it takes, I've had cases where it takes days. I think one of the keys that I found is build in those checks. Build in the checks where, for example, what we would do with that is, I would output the top percentile of predictions. I would look at the features for those, and I would see, how does that compare to the mean across the entire group? And so if we found, for example, in that case of the consumer data file that happened to have data leakage, what we were finding is, oh, wait, the average value or the average feature value for our top predictions was way, way higher, like orders of magnitude higher, and to the point where it just wasn't credible. And similarly, looking at feature importances and so forth, I think just planning to build all that stuff in your process in a way it's planning to do the debugging from the get-go. And fortunately, you know, when we're talking about how much time all this takes, this is something where, going back to my point of building software, turning this into a package where you just build this into something that then you can reuse across all your different models, hugely valuable. I mean, a lot of these just basic checks of like the relationships between your features and your outcomes beyond just basic feature importances, I think that's something that's worth doing for every model. Even if you don't spend a ton of time digging into it, it's good to have and be able to refer to. And if nothing else, it's also very helpful for explaining how your models work to people who aren't data scientists, who might not understand it, but you know, they can understand that, say, if somebody's volunteered for a campaign in the past, they're more likely to volunteer in the future. Being able to just say, you know, that 50% of people in that top bucket had been volunteers, you know, in the last cycle, that makes a lot of intuitive sense for somebody who's not a data scientist. So, you know, I think that's just something that should be part of a normal process. Others? Yep.
You had a great talk about fixing logic errors, data scientists supporting fixing those logic errors. What do you do about syntax errors, things that cause the system to crash? Are the data scientists on call at your organization, or is it the data engineer?
Well, we're a union shop, so nobody's on call. No, I'm on call. I'm the one non-union person, so if it's after hours, it's me. You know, realistically, though, like the restaurant inspection models, for example, which Ben was the person who made, and that's why I used him in that contact example. You know, that runs once a week. We deliver new predictions on Friday. It gets used, you know, starting Monday by our inspectional services department. So, you know, in terms of syntax errors, I mean, I think that's a very general programming question, and hopefully you've worked out the kinks before you put things into production like that. But yeah, this stuff always comes up. I think, you know, all the standard recommendations around things like unit tests and integration tests, you know, particularly apply to these sorts of models.
And do your data scientists build the unit tests and the integration?
We have an engineer for that.
Okay.
Yeah. Yep.
So I've building models like this, I've noticed over the longer someone stays in production, generally the more like complex the model gets, largely to kind of deal with a lot of the issues that you brought up. Do you have any kind of advice or for how you kind of deal with that, or is that something you've experienced as well?
Yeah, I mean, I'm just thinking of the fundraising models, you know, where it's very easy to add to an ensemble. You know, going back and forth between, you know, am I using extra trees or random forest? Oh, wait, I can use both. Oh, wait, I can build in gradient boosting. And, you know, eventually I've got like a dozen different algorithms in play. When I did that, I found out at the end, I went back and, you know, compared the performance in retrospect of the entire ensemble versus just picking the best of them, the best, you know, the best algorithm, and it actually wasn't that different. I think it just has to be a conscious choice to recognize that, you know, there's overkill in building in complexity, and I think dealing with all of these exceptions. Oh, yeah, one point though I think that is crucial that I didn't make earlier is try to solve the problems in your ETL process and your general data flows. One of the reasons we actually, when we had problems with fundraising models, what most often was the case was the data that got entered was bad, because a lot of that was being done by hand by our mail the vendor that sends the mail and the vendor that collects mail that comes in. You know, if there were data problems there, it would feed into the model and the model would break. And I think solving those problems at the source can help to avoid a lot of those ad hoc fixes along the way. Because we certainly had a lot of them. There was a lot of like, if the mailing is from this month, make this change to the coding. You know, this is one of those things where it's like getting to know your data is partly important because that will help you fix it. Others? Yeah.
Do you have any examples of like sustainable models or stuff you've worked on where you don't have an inbuilt feedback system, where you're sort of like creating predictions or you're doing whatever it is, but you don't necessarily have a way that like as your predictions are being as you're making your predictions, you automatically know like, oh, this worked, this didn't.
Well, I mean, you don't automatically know. You don't know unless it's tried. Like, for example, the phone contactability models. You know, we wouldn't know unless somebody actually tried that phone number. And so there were a lot of cases where, you know, for example, Massachusetts phone numbers suck in there because Massachusetts doesn't have a lot of competitive races, and so there weren't a lot of campaigns trying out those phone numbers. You know, I think if you're not getting it from anywhere, I don't know that it quite falls in this category of model. But certainly there'll be cases where you're getting feedback from a sort of narrow set, and you have to kind of make some assumptions about how that applies elsewhere. I think that kind of gets back to that point of making sure your model is responsive to differences in the patterns that it's observing. And if for example, the Senate race in Massachusetts next year ends up being super competitive and a ton of phone calls get made, then it should be, the model should be able to react to that and start fixing those numbers pretty quickly once we find, oh, wait, it's not actually working as we intended. Others? Yeah.
Say you have like a response model that you're about to deploy, and you can tell by profiling like your top leads that it's kind of just like a circle. These people are highly likely to respond, so you have bias in your data. How would you go about like introducing like a new segment to test? And obviously keep track of them.
I won't say that I've salted predictions before, but I won't say that I haven't either. I mean, just in the sense of if your model isn't giving you diversity and you need that for the model to work, then you need to be deliberate about adding in new data collection. And sometimes that might mean, the example I gave of the volunteer scores, where we knew we could give better targets than what we actually delivered. And the reason is for the sustainability of the model, it was important that we got data back from a wider set of people. And so that in part gets to that relationship you have between the data scientist and the stakeholder who's actually going to be using it. And it's important for the stakeholders to understand for a model like this that the data coming back is critical to making sure the model works long term. And so that, if they're not giving you money to go out and collect data, they have to be able to help in some other way, which might mean, going and calling phone numbers or inspecting restaurants or knocking on doors or whatever, in a case where you otherwise might not, because based on what you know now, that doesn't seem ideal, but it's important to the long-term success of the model. I think I'm getting the sign that's time to leave. So thank you all for attending, and hope you enjoyed.